you've got is this apparatus that I built. So what you've got is that you have these two aluminum plates. Aluminum is what's known as a non-ferrous material, which means that it's not attracted to magnets. So if I put this magnet anywhere near like the outside of this, there's no attractive force. But if I take this, which is a ferrous material, it's very sticky, okay? So this stuff, ferrous, it's magnetically attractive. This stuff isn't, okay? So in and of itself, this is not attracted to the magnet. But if I take this magnet and I move it in between the plates, I can make it move. But if I move it on the outside of the plates, the magic wand doesn't work. So one of the things that you're going to do is that you're first going to make a bunch of observations. Does this ever make the force, does it ever make it go faster? Like let's say, for example, I have it like this and I make it go through. Does that ever make it speed up? Does it always make it slow down? That's what you want to look at. If I move it slowly versus moving it quickly, does that impact the amount of force that's going to act on the system? So you're going to have different materials. Like you're going to have, where did it go? Should have been a square little piece of green paper, green film. That, okay? So this is magnetic film. So like if I put this up here, like you can see that magnet as it shows up like as a distortion on that paper. So if I have this on the outside, and I move this through it, you can see that going through that aluminum plate. So these are observations that you can make. What does it do? The speed of factor. Does it make it slow down? Does it make it speed up? Does it make any difference if it's on the inside? Does it make any difference if it's on the outside? Because any good scientific endeavor just starts with observations. Once you get that done, and you're going to have, that's going to be the opening salvo of your lab. Here's my initial observations. What you're ultimately going to try and do is find the amount of force acting on this magnet as it moves through the plate. That's your end game, okay? One of the tests that I'm going to tell you to do, the other ones are up to you, but one of them I'm going to specifically tell you what I want done. I'm not going to tell you how to do it, but I'm going to tell you what I want done. So the first thing that you want to do is that, and this is where a whole bunch of things that you've studied are going to come into play. You're going to take a string and, hold on. One second. I forgot I had these poles. Now, I'm going to use a 20-gram mass just to kind of show you what's going to happen. So, I'm going to put a 20-gram mass on the end of the string, like this. And what I'm going to do is that I'm going to let this fall a certain distance. I don't care what the distance is, that's up to you to decide. But what you want to do is you want to let it fall a certain distance so that that weight hits the ground, and then this is going to roll at a constant velocity. So this is where everything that you've studied before comes into play. You're going to know, and this is up to you to decide. You can put whatever weight you want on the end. Don't use 1 kilogram mass, that's going to be a bit much. So you're going to let this fall. You're going to find the mass of this cart. You're going to know the mass of on the end. You're going to know how far it's going to fall. You're going to be able to calculate, and this is what I'm going to very much judge you on. How do you calculate the theoretical acceleration of this cart when that mass is falling? What are you going to use? How far are you going to let it roll? Once you get that value, and you need to decide when you're writing this up, where are you going to measure distances from? Are you going to measure from the back of the cart? Are you going to measure from the front of the cart? Are you going to measure from the front of the aluminum frame? Are you going to measure from the back of the aluminum? I don't care, okay? I'm not going to tell you what to measure, but I'm just going to tell you what I want as the end game. So you're going to let this thing fall a certain distance. And you're going to be able to say, based upon that acceleration and how far it travels, this should be the velocity of this cart when that hits the ground, okay? So you're going to know an acceleration and you're going to know a distance. Based upon that, you're going to say, theoretically, it's going to be traveling 2.20 meters per second, whatever it is, okay? Then you need to find a way to verify that. So because of the fact that we're assuming that this thing is going to be traveling at a constant velocity, because we're going to assume that it's frictionless, you can say, okay, it's going to be traveling at 2.2 meters per second, theoretically. But then you can measure how far it goes after it hits the ground. You can measure time. So if you assume that it's moving at a constant velocity, you can say, okay, after it hits the ground, I'm going to let it travel another 20 centimeters. I'm going to know the distance, I'm going to measure the time, and I'm going to compare that velocity, the actual measured velocity, to the theoretical velocity. Tomorrow I'll also show you, I'm going to have something called a sonic ranger. That allows you to mathematically determine, based upon equipment, a velocity as well. So you can use that and go, hey, the sonic ranger says it's going this fast. My calculation of velocity and time, or distance and time, says it's going this fast. My theoretical acceleration says it should be going this fast. Okay, so you want to have three kind of different, at least two, if not three bits of data that say, hey, here's what's going to happen. Now, here's the point of the story. Can you put, Jacob, can you put that on?
Yeah.
So here's the main point of the story. Because you're ultimately going to try and find the force generated from this. Here's the end game. So you're going to set this up where when that hits, put that back on. When that hits the ground like that, that's when you want, at a minimum, this magnet to start interacting with this. You can have it further down, but whatever you do, don't have this magnet interact with this aluminum before it hits the ground, because then that's going to act as an opposing force to your motion. So you're going to have it falling, boom, it's going to hit the ground. Now, what's the final velocity going to be? Zero. Are you going to know the initial velocity when it starts to go in?
Yes.
What can you measure?
Time and distance.
Time and distance. So you can measure how long it takes to stop. You can measure the distance that it takes to stop. That's the type of thing that you can do. Then you can get the acceleration with the magnet. Guess what you can find from there? Force. Because then you know the mass, you know the acceleration, there you go. Because that's what you're ultimately after, is what's going to be the force created by the magnet in a moving system. Now, here's what you don't want to have happen. Don't have this thing going so fast that it blows through it. You want this thing to stop within this, because otherwise you're going to have to guess the velocity when it exits, and that's going to get real ugly. It's going to be much simpler if you have it going a certain speed where this thing will stop within that distance of that magnet interacting with it. So maybe something like this, boom, that hits, stops it. Make sure that that magnet isn't like physically rubbing against the sides of the aluminum, because then you don't know if it's the magnet that's stopping or if it's friction with the sides that's stopping it. So as that rolls through, and you want it down about maybe something like that. So you're going to have this, boom. Well, I say that, and then I hit the sides. You get the idea. Just try that over time.
Dang.
Close enough. You got the idea. All right, so here's the story. I'm done. Okay? So you've got all of today, the rest of today, and all of tomorrow, and Friday. This is just one of the things that you need to do.
Oh.
There are others. But this will, if you can get this procedure figured out today, figure out what weights you're going to use, figuring out the distances. Now, when you're writing your procedure, here's your guiding light. Number one, do not write your procedure as a paragraph. You are not in English class. You are not writing an essay. You're going to say, step one, do this. Step two, do this. Step three, do this. The mark of any good scientific procedure is that Dylan should be able to take the procedure written by Jacob and replicate his results. That's the mark of any good procedure. So, I'm going to be grading this. If you just tell me, hey, drop the mass and let it roll, I don't know how far I'm going to drop it. I don't know what mass I'm going to put on the end of it. Where do I put the cart? Do I put the cart at the 1 centimeter mark? Do I put it at the 100 meter mark? Am I going off the front? Am I going off the back? So when you're writing that procedure, you want to write it so any other group in this room can take your procedure and replicate your results. Okay? That's how you want to view it. Do not view it through the prism of somebody in your own group understanding it, because they're working with you. They're knowing what you have. The trick is to write it so that somebody else who's not in your group but has a basic understanding of physics can replicate your results. Now, in the spring, we'll actually study why this works. It's called an eddy current. Okay? So in the spring, when we do electromagnetic theory, we'll actually go through the mechanism and you'll see why this works. The short version is that when this goes through, it creates a changing magnetic field. The aluminum plates flip out. They also create a magnetic field that opposes the motion. Don't worry about that, not part of the story. You're just trying to figure the value of the force. Okay, you're on your own.